Alright, now we will start on doing the shear diagram and the moment diagram. And just to point out, this is A and this is B. So let's start off. So if we were to draw the moment or the shear diagram, so this is the shear force and this is the X or the direction that way. So what's the shear in this part of the beam? Well, the A component is 400 kilonewtons. So that means the shear in this part until it reaches another force is 400 kilonewtons. And we don't reach another force until we get right here. Oops. So that is 400 kilonewtons. So there is a shear force all the way across here of 400 kilonewtons. Now the shear starts to change in this area. And we can't treat this as one force. We have to treat it because each part of each little section of this, each very minute section of this has a different shear than any other part of it. So the simplest way is to draw the line straight down from it, and we will see that this is 1,000 kilonewtons, so the shear changes by 1,000 kilonewtons, and it's going down a negative 1,000 kilonewtons. So it will go down to 600, a negative 600 kilonewtons. So that's probably somewhere about right there. So then we just connect these lines. Oops, close enough. So we connect those lines, and now this part of the beam, it only has a force of a negative 600 kilonewtons until we get to that point. So that is another 600 kilonewtons. And notice that our By is 600 kilonewtons, so that we did good. So getting to this point of a negative 600 kilonewtons meant that we did it right so far. So let's move on. So that's our shear diagram. Let's move on to our moment diagram. And let's use green. So moment, and this is our X. Try to make it a little straighter. So let's just put in our points. Whoops. And remember, all the moment is the integration of the shear diagram, or the shear force versus the distance. So right here, there's no area. So right here, remember the moment is just the area under the line. And right there, there's no area, so this is 0. So the area until until this point is the total area under this. That's 400 kilonewtons times 2 meters. So that gives us 800 kilonewton meters. So we'll say maybe that's a point right there. Again, that's 800 kilonewton meters. So all the way right there. So that is a straight line. The reason it's a straight line is because the area is increasing equally. So it's linear. Now, we got to find what this distance is. What distance is that? So if we remember that these two triangles are the same, except they're just, this one's much smaller than this one. So if we know what this distance is, which is 2 meters, and we know what this length is, which is 1,000 kilonewtons, and then we know what this distance is, then we can find out what this distance is. So we're going to call that X. So we have 2 meters over 1,000 kilonewtons. Oops, kilonewtons. And that must equal this distance, X, divided by whatever this distance is, 400 kilonewtons. 400 kilonewtons. So that is equal to, our X is equal to, so if we move the 400 over there, so we get 800 kilonewtons meters divided by 1,000 kilonewton meters. We just get x is equal to 0.8 meters. So erase that. So this distance is 0.8 meters, and that means this distance is 1.2 meters. So if we remember that the area of a triangle is the 1/2 the height, which is 400 kilonewtons, times the base, which is 0.8 meters, that will give us 160 kilonewton meters, sorry. So now we add 160 kilonewton meters to find out where it is on this point. So 800 plus 160 is 960. So we'll say maybe right there, 900, actually, so we'll just go straight across. That is 960, 960 kilonewton meters, that point right there. Now notice that it's most of the area is coming from this side, so this is still pretty much a straight line. But this point right here, there's not very much area being added, so this is kind of a flat line. So it's actually kind of curved. It's no longer, I mean, that looks like a straight line, but it's curved. So pretend it's curved. You'll definitely see it when we do the next spot. So now let's find the area right here. So let's get the area of that. So that is, again, 1/2 times the height, which is a negative 600 kilonewtons, times 1.2 meters, 2 meters, and that is equal to 360 negative 360 kilonewton meters. So now we subtract 360 kilonewtons from 960, and that should give us 600. So fine. So that's probably 4. So this is probably 6. So we'll just go across right there. So that's 600 kilonewton meters. Now you may be tempted again to draw a straight line, but it's curved, remember, because there's very little area being added right here. So that's still kind of a straight line that way. But there's a lot of area right here, so this is going up pretty quickly. So it's going up. So then to connect these, you just draw a nice little curve. And that it's not really curvy, but so we got that nice curve, and then we just need to find this area. And that area is the negative 600 kilonewtons times 1 meter, and that's a negative, so that's then a negative 600 kilonewton meters, and that will take us right there. This was a pretty messy video. I apologize for that. The things you need to really focus in on is, why is this a straight line? Why is this curved? Why is that curved? And hopefully I did a decent job in explaining that most of the area is being added in right here, where this is adding very little area. So that's pretty much a flat plateau right there. And I mean, there's just very little area relative. And again, this is flat like that. So I don't know, just really focus in on why those are straight and curved lines. And if you have any questions, please leave them in the description or the comments below.